Well,
Okay, good afternoon, everyone.
Good afternoon.
All right, so I've laid out the next few days here for us. We're going to start class today with a quiz. It's going to be a poll that I take, but it will record your responses, and then I'll go back and look at those and whether or not they're correct or not. So this is not it will not be an anonymous poll. It will be associated with you. So I'm going to basically show you some pictures and ask you some questions, and you'll have 2 minutes to answer those. It's not much time, but see how you do. And then we're going to start 2.3, or we're going to get through 2.3, start 2.4, finish up 2.4, start 2.5 on Thursday. Then a week from today is your test. So that's the plan. See how things go. Any questions? Okay, so you ready?
Where do we go to do this properly?
Yeah, just wait. You'll see a poll come up in a minute. Let me show you the quiz first. Make sure you can see this. So I'm giving you some graphs here. So you make these a little bit bigger. So there's two problems. It says for these two problems, choose whether the blue or the green graph is the derivative of the red graph. So you're given the red graph, that's your function f. And then either the blue one or the green one is its derivative. So you have to figure that out. And if you have no idea, then you've got a 50% chance on each one, I guess, right? So here comes the poll. I'll start the clock here.
Excuse me, can you repeat the question?
It's written down here. For these two problems, choose whether the blue or the green graph is the derivative of the red graph. Hold on, I should have had my poll here. Hold on. What the hell, man? Okay, well, I guess you're going to have a little bit more time. Hold on. Well, you're going to have to wait, I guess. So you're either going to answer that you think number one, it's the blue one, or you're going to say on number one, it's the red one. And on, I'm sorry, not red, green. And then on number two, you're either going to say it's the blue one, or you're going to say, I guess I could have done 2 questions, but this will work. Green. So you're going to select 2 of these, right? You're either saying number one, it's the blue or the green, and then number 2, either the blue or the green. So you should have 2 selections. Make sense or not?
Makes sense to me.
Hold on, still didn't go right here. I got to delete that one. There we go. Save. Okay, there we go. Okay, you should have the poll. Yes, I need to show you the pictures. Huh?
Yeah, can we see the picture again?
There you go. Okay, you have 1 minute. All right, 10 seconds. Okay, so let's see, let's look at the results. You should be able to see the results. So number one, 86% of you said green, and number two, 86% of you said blue. Let's see what's correct. I'll turn my video back on. Okay, there we go. So I should have this here. Where is it? There we go. And let's look at the first problem. That was the first problem, right? Let me just double check. No, that was the second one. I have them backwards. All right, this was the first problem. Yeah, okay, so let's talk about this. The red one is the original function. We're looking to see whether or not the green or the blue was the derivative. So I think the easiest way to go about this would be to go onto the red function where you know that the slope of the tangent line is 0. So that would be like right here, you know that the slope of the tangent line is 0. Also right here, the slope of the tangent line is 0. And here, the slope of the tangent line is 0. And that means your derivative must have x-intercepts there. And only the green one has x-intercepts at that same value right here, same x value here and here. So green. Now the other one, you could do the exact same thing on. And this quiz wasn't designed to be difficult. It's actually going to be something I'm going to use later today. I need to illustrate something, so I'm going to use these two pictures. But I thought it'd be a fun quiz. No. Okay, here the slope of tangent line is 0, slope of tangent line is 0, slope of tangent line is 0. And so we're looking for which graph goes through the x-axis at these values. So here, boom, here, and here. So you really don't even need to check anything else. I mean, there's only two choices, so it can only be the blue one here. So green for 1 and blue for 2 is correct. Okay, any questions?
I had a quick question, sir.
Yes.
So, is there another way, like, you can find, except for the like x-intercepts? Like, you see how the red one is our major function. So you see how so we're going based off the blue and green line. I remember from last class, another way we can tell is whenever the slope is going down, the derivative has to be going down as well.
No, the derivative doesn't have to be going down.
Or it has to be negative, right?
It has to be negative. Yeah, so like what you're saying, what I could have done is this. I could have looked right here, just in this section of this function, right? From -2, right? From -2 to 0, my original function is going down, which means the derivative would have to be negative, which means it's below the x-axis. And you can tell right here, the green one is above the x-axis, right? That's no good. It's got to be the blue one here that is below, right? Negative values for the derivative corresponds to the original function going down. The original function going down corresponds to the derivative of the function being negative or below the x-axis. So yes, you could have done it that way also. I think it's a little harder because you have to, make sure. I mean, this would have been, as soon as we saw it, we would have been done, right? Because this is positive.
Right.
Does that address your question?
Yes, sir, it does. Thank you.
Okay. Any others? Okay, all right, let's move on. So we are moving into chapter 2, section 3, basic differentiation formulas. So really, we know right now that if someone gives us a function f of x, we should be able to find the slope of the tangent line so long as we can evaluate that limit, right? We need to be able to do, right now, the definition of the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. And if you did your homework, you realize that that can be messy, right? But now, okay, we finally get to move on past this torture. And so we're going to have some shortcut formulas. And I told you these were coming, okay? So here they are. Today we start with them. These shortcut formulas are going to make our lives so much easier, all right? But as I promised also, once we get the formulas, then we get harder functions. So it's kind of, be careful what you wish for, right? Because you might just get it. And so we're getting the formulas, but now things are going to get tougher. So let's first establish the formulas, all right? What are the basic differentiation formulas that everybody needs to learn? All right, there's a few of them. So the first one is the derivative of a constant. Okay, so the way I wrote this is d dx. I'm using a notation we went over before. D dx and then c here equals 0. So c is just, when we say a constant, what we mean, right, is basically any number, okay? So if you take the derivative of any number, you should get 0. Another way to look at this is to say, hey, let's say we had a function, f of x, that was a constant. Let's just call it c. Then what this formula is establishing is that the derivative of that would then be 0. That's just another way of writing what this means, right? Another way you might see me do it is to say this: take a constant and then put a prime on it like that. That means take the derivative of the constant and you get 0. So I'm just showing you like different ways of saying the same exact thing with different notations, right? All of these mean the same thing. So let's establish this formula. Let's establish it visually, okay? I think we can convince ourselves that this is true. Let me do one more notation. If I tell you that y is a constant, okay, then what we're saying is that the derivative of that is 0. So what I'm going to do is I'm going to go to my graphing utility. I'm going to graph y is equal to a constant, and let's just look at it and convince ourselves why the derivative is always 0. I think this is, well, this is the easiest one to understand. Where is it? Where's my, sorry, I just started a new one. Y equals a constant. There we go. I'm graphing a constant, right? It doesn't matter what the constant is. All the constant does is moves this horizontal line up or down. If I go to any point on this line, right, any x value I want, go up and look at the slope of the tangent line, it's going to be parallel to the line itself, which has a slope of 0, right? No matter where I go. Slope 0. So does it make sense that the derivative of a constant would be 0? Do I need to illustrate that more, or is everyone comfortable with that idea?
I got it.
Okay, that one I'm going to do visually. Let's look at the next rule. Maybe I should give you all a specific example, although it's not that that difficult to understand. Let's see. For a specific example, right? If I say f of x equals pi, and then I ask you to find f prime of x, your answer would be what?
0.
0, okay? Because pi, even though it's weird, right? Pi is just a number. 3.1415, doesn't matter, it's a constant, the derivative of that would be 0. If this pi were a 10, the derivative would be 0. If it was -5, it would be 0, right? Doesn't matter. Constant by itself, derivative 0, we're done. We happy? That's a nice one, right? Easy. Okay, the next rule is that the derivative of x is 1. The derivative of x is 1. So let me write that down. The derivative of x is 1. Another way of writing that would be if f of x equals the function x itself, the derivative of that would be 1. Another way of writing that would be that if y is x, then the derivative of that is 1. And then another way I could write it is just put x with a prime mark on it and then say that's equal to 1. All of those, again, are like different notations for the same exact idea. Let's convince ourselves, all right? Let's go graph y equals x. And again, I think this one's easy to understand also, because if I just graph y equals x, we should all recognize that from college algebra as the identity function. Remember it being called that, the identity? It's that perfect diagonal line. And the idea here is that if you go to any point x and you go up to your graph, the slope of the tangent line, again, will be parallel to the line itself. And the slope of this line, if the line is y equals x, the slope of the line is the number in front of the x, which would in this case be 1, right? So the derivative should be 1 all the time. That clear? Visually, make sense?
Yeah, makes sense.
Any questions?
Could that shortcut also be used? You can remember where you go down a exponent, a power, to where it's basically just going to be 1.
Yeah, remind me of that, Ethan. I'll show you that because I think we're almost to that rule, okay? We're almost there. But just remind me, I'll come back and verify that. Okay, so next rule. So the first two, pretty clean, right? First two make sense visually. Okay, here it is. The almighty power rule, okay? This is a huge rule right here. I'm gonna copy it. Well, I'll just write it on the next page. Let me, so this is the next one. This one is the power rule. You can call it the almighty power rule if you'd like. No one's gonna get mad. Now I will add one thing to this for differentiation. This is the rule we use when we're trying to take the derivative of x raised to a power, when we're trying to take the derivative of x to a power. In Cal 2, there's another power rule for when you're trying to do the antiderivative of a function. We'll actually learn that rule at the very end of class. But this is the power rule for differentiation. All right, so here's how the rule works. If we're trying to take the derivative, that's what this means, right? Take the derivative of what? X raised to any power. Any power. That means it could be raised to the second power, third power, fifth power, the 1/2 power, the -10 power. It does not matter what the power is, okay? Any power of x. The derivative of this will be n x to the n minus 1. N times, that's a multiplication, n times x to the n minus 1 is the derivative. So that means that another notation for this would be if f of x is x to the n, then the derivative of that is n times x to the n minus 1. Another notation would be if y equals x to the n, then y prime would be n x to the n minus 1. And then the last kind of notation is that if you take x to the n and you take its derivative, you get n x to the n minus 1. So this is the rule I talked to you about before, that what this rule says you do is you take this power out here, right? Let me write this in a different place. X to the n, if we're trying to take the derivative of this, the rule says you take this power and you just kind of like drop it down in front of the x. So you put n times x. And then you basically take that number and subtract 1 from it. So I take that n and I subtract 1. Let me show you a specific example. Okay, and then I still haven't proven this rule is true, right? I'm just telling you it's true. The previous two, I kind of visually showed you that they're true, didn't I? And I think everyone was like, yeah, that makes sense. All right. I have not proven that this is true, but let's just do an example. Let's just say that we have f of x is x to the 6th power. And I want to know the derivative, right? Then the derivative will be 6 comes out, x to the 6 minus 1. We all know that 6 minus 1 is 5. So 6x to the 5th is the answer. Okay? Don't make it more complicated than it has to be. You're just pulling the power out and subtracting 1 and you're done.
So question,
Yes.
this might be getting a little bit ahead of myself, but what if it's something like x to the 6th minus 1 or x to the 6th plus x squared?
Yeah, okay, good.
just-
That'll be, it's in these rules. We're going to get to it today in just a minute. Yeah, so we're
Okay,
building.
gotcha.
Yeah, right now we're starting with single terms. And then we're going to ask ourselves, well, what if you have addition and subtraction between terms, right? Like, what's the rule? And what if you have two things being multiplied? What's the rule? What if they're divided? What's the rule? Okay, so we're going to build to it.
Good.
Let me give you one more. What's that? You good?
Yep, nope, we're gonna get to it. I'm gonna stop asking questions.
Well, don't stop asking questions, but I'll let you know if it's coming.
Stop asking about the things that you just specified we're gonna get to.
Yeah, if you don't know they're coming though, keep asking because you never know. All right, so look at this. Square root of x. All right, you have to understand that this is x to a power, right? This is x to the 1/2 power. And so according to this rule, the derivative of this, I'm going to take that 1/2 out front. I'm going to take the x, then I'm going to take that 1/2 and subtract 1. Now, throughout the rest of this class and into Cal 2, you will be subtracting 1 from numbers and adding 1 to numbers a lot. Okay, a lot. So you need to get good at subtracting 1 and adding 1 to fractions, because if you're slow with this, it's going to slow you down on tests. You just kind of have to get really fast with this. So the way I always think about it is, 1, I look at the other fraction, I get a common denominator. I always look at this as being like 2/2, right? Instead of 1, I look at it as 2/2. Then I just subtract across the top. So I get 1/2 x to the 1 minus 2 is -1. Then they keep the common denominator, so 1/2 x to the -1/2, right? And now that's your answer, right? That's the derivative of the square root of x, 1/2 x to the -1/2. We could box that up, we could be happy with that and move on. But this square root function, we take the derivative of square roots a lot in this class. So I want to show you another version of this same answer. I'm going to rewrite it this way. So what I'm doing here is I'm just using properties of exponents, that if you have a negative exponent on something, right, x to a negative number, you can drop that down to the denominator and make it x to that positive number. These are properties of exponents. You remember that from college algebra? So that's the same answer, right? And then I'm going to go one step further and I'm going to rewrite x to the 1/2 on the bottom as the square root of x. Put a star next to this. The way I'd like for you to remember this, I'm going to do it in blue. The derivative of the square root of x is equal to 1/2 root x. Let's say that again. The derivative of the square root of x is 1/2 root x. The derivative of the square root of x is 1/2 root x. We'll do it one more time. The derivative of the square root of x is 1/2 root x. right?
I didn't like us memorizing.
No, it's a song. You just, you're singing it. Now, this is one of those things you should just burn in, because again, it comes up a lot, the square root, and it'll just, again, slow you down if you're sitting there having to do all this stuff every single time. Let's do another one. I still haven't proven this rule to you, have I? I have not proven it to you. We're just taking it on faith right now. What about, instead of the square root of x, the cube root of x? Do you think that this will turn in, like if we follow the same pattern from the other one, do you think this turns into 1/3 cube root of x maybe? Like you see how this one, we got the 1/2 because the 1/2 came out, right? So maybe this will be a 1/3 comes out.
I could see that if it was.
Seems maybe like reasonable.
Wouldn't it be to 2/3, right?
Yeah, see, it's not going to work. So first things first, let's convert this over. Everyone hopefully comfortable with the idea that's x to the 1/3, right? That's the original function. Now the derivative. So 1/3 comes out. X to the 1/3 take away 1. But I rewrite 1 as what?
2/3.
3/3.
3 this time.
Negative 2/3.
And then subtract 1 take away 3 is -2. So we get 1/3 x to the -2/3. -2/3.
So it would be 2/3 cube root x.
No, the 2 is on the exponent. So you'll just have a 1 up here. The 3 will come down.
Oh.
You'll have x to the 2/3 down here. So when you drop that down,
Cube root x
it
squared.
becomes +2/3, right? The 2 comes with it though. And then you could turn that, if you wanted to, into 1/3, and then this would be the cube root of x squared. Now you don't need to memorize this one. I just wanted to make sure you understand there's not, don't sit there and try and establish a pattern for all roots with just one. Each one is different, but this one you need to memorize. The one with the derivative of the square root of x is 1/2 root x, right? That one you need to know. Let's do a couple of more examples before we get into why it's true, because that's going to take me a little while to show you. Okay, so any questions before I move to another example? Okay, how about this? What if f of x is 1/x to the 5th power?
We can turn that to x to the -5th, right?
You could turn that into x to the -5th. Everyone agree? You could bring that x to the 5th back up. Now, I'm going to do something. Don't write this down. I'm going to do something though. And I want you to tell me if you can tell what I just did. What did I do?
Derivative of a constant is 0.
So I did the derivative of the top, right? And the top is 1, right? So the derivative of a constant is 0. We know that, right? Derivative of constant is 0. So I took the derivative on the top and got that. And then I took derivative on the bottom and I got that. I used the power rule on the bottom, didn't I? And so 0 over anything is going to be 0. So I came up with 0, and that is wrong. It's wrong in many ways. Now I'll tell you why it's wrong. Right now, the only rules we have are that if you have a constant by itself, the derivative is 0, right? If we have x by itself, the derivative is 1. If we have x to a power, the derivative is n times x to the n minus 1. So we bring the power down, subtract 1. Have I given you any rule on how to deal with quotients when you have a fraction? Have I told you when you have a fraction, you can take the derivative of the top and bottom separately? Have I told you that? I've not told you that, right? Life would be nice, okay? If this was true, if I could do the derivative of the top and bottom like this, if that was allowed, calculus would be so much easier, okay? Trust me, calculus would be a lot easier if that was the rule. It's not the rule, okay? I haven't shown you the rule yet. So don't start doing things that you aren't allowed to do and just assume it's a certain way. You have to be real careful with the rules because they guide you, right? You can't just make up your own. So right now we have no way of dealing with a quotient. So what we do, okay, what we do instead is we rewrite the function so that it doesn't look like a quotient. And so that it looks like x to a power. So we bring that x to the fifth up to make it x to negative 5. Now I have a rule for that, right? I have a rule that says if I have x to any power, the derivative of that will be, well, bring the power out front, right? Negative 5, x to the negative 5, and then we want to take away 1. And just be careful there, right? You're subtracting 1 from negative 5, which gives you negative 6, right? And that answer would be fine. If you wanted to, you could rewrite it like this. I don't care. I would take both of those for full credit. They're the same thing. I just want you to be comfortable with the idea that you could take this x to the negative 6 and drop it below the negative 5 and make it x to the 6 on the bottom. Questions? Maddie, all right? Okay.
This is kind of where we like separate from limits, right? Because before on limits, we could like separate the numerators and denominators.
Yeah, good. I'm glad you brought that up. So I think what Ethan's saying is like when we did limits, right? You could do the limit of the top and bottom separately, couldn't you? When we were doing limits. Let me give you an example. If I was doing limit x approached 2 of x squared minus 4 over x minus 2, I told you, oh, just direct substitute, right? Take that 2, plug it into the top and into the bottom and figure out what's happening. You could do them, you know, do the top and do the bottom, right? Just do them. The derivative does not work that way. When you take a derivative, you can't just do derivative of top, derivative of bottom. You can't, right? Limits, you could. That's why when we were first learning limits, I told you about the limit laws. And we didn't get too deep into it. I showed them to you. And I said, basically, everything with limits behaves the way you want it to behave, right? If you have two things added together and you take a limit, you can take a limit of each one. If you have a quotient and you take the limit, you can do top and bottom separately. If you have a product, you can do them separately. Once you get to derivatives, that's when all bets are off and it changes. All right, here we go. I still haven't proved it to you. But this one, 1 over the 5th root of x squared. Let's find the derivative of this. So again, we cannot change this, right? We cannot change this into, we can't do top and bottom separately, right? So we can rewrite it as x to what power?
X to the 2/5.
2/5. And then we can go one more step and bring that up as a negative 2/5. And now we can apply the rule, right? Now at this point. So our derivative should be negative 2/5 x to the negative 2/5 minus 1. But instead of 1, what am I going to subtract?
Negative 5 over 5.
5 over 5, right? And then when you subtract across the top, you go negative 2, take away 5, which would give you negative 7, right? Negative 7 over 5. Which would be a perfectly fine answer. But I'm just, again, going to show you what else you could do. You could leave the negative 2 on top, leave the 5 on the bottom, drop that x down as a positive 7/5. That would be fine also. Or you could go even further and you could just rewrite that in radical notation, 5th root of x to the 7. And you can actually go further than that, but I'm just going to stop here. Because you have 7 of these in here and you have 5th root, so you could actually pop an x out, but I'm just going to leave it.
I have a question.
Mhm.
Why is it positive 7/5 when we drop it down?
Why is it what? That's just a property of exponents, that if you have x to the negative n, that's the same as 1 over x to the positive n. This is from college algebra. So like if you write x to the -2, that really means 1 over x squared.
Okay,
Would you
thanks.
would you recommend getting like really comfortable with those different ways of representing the those exponents like that?
I would definitely not steer away from it. I mean, you won't be like dead in the water if you can't do it, you know what I'm saying? But it will benefit you to see how an expression, if you manipulate it, can look a lot different than it does, you know, like if you look at this doesn't look, I mean, it's similar, but there's a big difference between the way these two look. And when we start to try and combine things together, our expressions can start to look really weird. And so you just have to be comfortable with the algebra. One of the challenges I think you'll have is seeing if you can make your answers look like the book's answers. Because usually your answer is going to look different than the book until you do the appropriate algebra to make it look like theirs, which is, I think, a good exercise. Try and make your answer look like the book's. Does that answer your question? No? Okay.
Yeah.
Are you ready to see why the rule is the rule? So here's the problem. In the previous two that I showed you, right? When y was a constant, well, we know what all constant functions look like, right? They're just flat lines like this. So I know the derivative is always 0 because it just makes sense that it's always flat, right? And then when it was y was x, right? Y equals x, that was kind of easy because even with this, even if I move that graph around up and down, the slope still stays the same, right? So the derivative of x should always be 1. But when we're talking about x to the n power, where n can be anything, those all look different, don't they? Let me try and graph x to the n. I don't know how the computer's going to do with this. Y equals x raised to the n. It's going to let me add a slider. Okay. So there's n is 1. Okay, so this is x to the first power, right? Let's just do integers for right now. There's x to the first power, x squared, right? X cubed, x to the 4th, x to the 5th, x to the 6th, x to the 7th, right? Let's do some negatives. X to the -1, that's 1 over x, right? X to the -1, it's 1 over x. This is 1 over x squared, 1 over x cubed, 1 over x to the 4th. Would you agree that all of these are going to have different derivatives? Like they all have different slopes at different places. Like there's nothing uniform about these. Y'all agree with that? So I can't convince you visually. I'd have to go through each one and convince you, wouldn't I? Which we don't have enough time because there's an infinite number of n's. And that's just n being an integer. Let me let n be any number because I said the formula works for n being any number. This is going to get weird. I don't know what's going to happen. Oh, it's working. Okay. Oh. There's some, well, that's cool. Okay, here we go. Pretty neat. Okay, all sorts. So this x to the n is just a family of all these different functions. And so our derivative is going to depend on the n, isn't it? Our derivative should depend on the n we have. And it turns out that all you do is take the n out front and reduce the power by 1 and you got it, okay? But why, right? Why? You ready to see why? Was there a question? I thought I heard something. No? Sorry, sometimes I write math and I forget and I just automatically do it. This capital S with a line under it like that, in math, that stands for the word suppose. Okay. Suppose f of x equals x to the nth power, all right? WTS. That in math stands for want to show. Mathematicians like to abbreviate, okay? I don't know why, we just do. Okay, I want to show you right now that the derivative of this is n x to the n minus 1, okay? I'm going to try and prove that to you right now. So we're supposing that we're given a function x to the n, and I want to show you that the derivative of that is this, okay? You ready? I'm going to show it to you. So here's how I'm going to do it. Well, first I start out with what the derivative of any function is. The derivative of any function is the limit as h goes to 0 of f of x plus h minus f of x all over h, right? That is the general formula for the derivative of any function, right? We've established that already. Now, the function we are talking about is this one, right, in yellow. So if I ask you to take x plus h and plug it into this function, what will that function spit out?
X plus h to the nth power.
X plus h, the whole thing to the nth power, right? Okay, so let me continue. Limit h goes to 0. This will spit out x plus h to the nth power. That's this piece here. Then I subtract from that. So I'm subtracting what? F of x. Well, what's f of x?
X to the n.
X to the n. Okay, that's x to the n. All right, over, boy, this is actually pretty clean looking, isn't it? That's not so bad looking. All over h. Yeah. Here's the problem. X plus h to the n, you cannot just raise x to the n and h to the n, put a plus sign between them. You can't do that. You'd have to multiply this out. X plus h times x plus h times x plus h n times, right? But we don't know what n is. But
Isn't it 1?
what's that?
Isn't n 1?
No, n is n, right? I didn't tell you what n is. N can be any number. Okay, that's the whole point of this, is that n is free to, if n was 1, this problem we'd be done. If n was 1, right? What would happen if n was 1? Just take this, what would happen if n is 1?
X would subtract from x and you'd have h over h.
H over H, 1.
You'd have h over h, which is 1, right? But that matches what we said earlier, right? What is the derivative of x?
Yeah, I was gonna say, like, that's a mathematical proof of the derivative of x right there.
Which I did not show you because I felt I could convince you with the picture, right? Okay, so x plus h to the n, we're stuck with this. We go back to last class. I did this Pascal's triangle, remember that? It was for a reason. I tried to get you to establish a pattern in this. Remember this? So the pattern was that if you have x plus h to a power, let's say 6, if we looked at what's happening to the x's, we'll start with x to the 6th, then x to the 5th, 4th, 3rd, squared, x, gone, right? That was the pattern. The powers start to drop off. With the h's, we don't have an h, there's an h squared, h cubed, h to the 4th, h to the 6th, right? Blah, blah, blah. It builds up, yes? Then the numbers, all these numbers came from that Pascal's triangle thing right here, right? Yes? So I want you to pay attention to something. No matter which one we were in, if we were in raised to the 0, 1, 2, 3, 4, no matter which one we were in, do you agree that the first numbers were always ones? Yes?
Yeah.
Okay. Do you agree that the second numbers were always the power we were raising to? In other words, like this 6 was 6, that 5, 5, that 4, 4, right? That, sorry, I mentioned the wrong place. That 4 was 4, that 3 was 3, that 2 was 2, that 1 actually turned out to be that one. So the second number, right? The second number is always the power that we're raising the x plus h to. Do y'all agree with that?
Yeah.
Okay, that's all I need. As long as you agree with that, we're in business. Okay, here we go. So let me recap. If we were to take, well, let's just do it. Shit. let's just do it right here. I'm gonna move this out of my way. Okay, so let's say we had x plus h to the nth power. Okay, what can you tell me about the very first term? What would it be?
1. Be
One.
1x to the n.
1x to the n. Okay, agreed. Yeah?
Yeah.
Plus, okay, now tell me about the number in front.
Would that
N
be
to the x.
yeah
That
That'll
would
be
be,
in
what's the power here?
in
N.
So we would have n, okay?
so in
Now,
times
what power
x
on x?
to be in minus 1.
It'd be one less than what we started with, right? Because the powers on x come down. So if this was 6, this is 6 minus 1, right? This one would be 6 minus 2, this would be 6 minus 3. So the power starts to come down. So this power would be whatever the n was minus 1, right? Now, do we have an h?
Yeah, would it
We have
just
an
be
h
h
on
to
this
the
one, right? H
Yeah.
here. Okay, plus. Now, the next number, I don't know what it is, and actually, I don't care. All right, and you're not gonna need to care either. You'll see why in a minute. So I'm gonna leave a blank spot. This is a number which I don't know, and I don't care what it is. But I can tell you that the power on x has now come down by 2, right? Started out with the nth power, took 1 away. Now we're taking 2 away, right? How about the power on the h?
h squared.
Comes up. So now we have h squared. Is everyone following this? Kind of following this? The next one is going to be some number, I don't care, x to the n. This time I'm taking away 3 because I'm on the third subtraction, right? Here I was n, I took 1 away from n, took 2 away from n, took 3 away from n. Now I'm going to have h what?
The third.
Third power. Plus, now this is going to keep happening, right? It's going to just keep dot, dot, dot. So I'm going to say dot, 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 dot. Who cares what's happening? Let's talk about the other end. What is the last piece of this?
Going to be in
We
oh no,
H
it's
to
gonna
the
be
one
h to the n.
h to the nth power. Because on the end, right, the h is the same power as what we started with. So that'll be h to the n. There won't be any x's there, right? The one in front of it will be h to the n minus 1, right? Because if this is 6, this was 5 on the h. How many x's here?
Just 1.
Just 1. And then some number in front of that, right? I don't know what the
Wouldn't that
number is.
be in?
It actually is n, but I don't even care. It's not going to matter.
Well,
And then we have a bunch of shit in front of that, and I don't care what that is. Okay,
could I speculate real fast?
what that number is right here?
No, not what that is, but I think I see what's going to happen.
Let me write it out first. Let me write it all out. So this is what x plus h to the n looks like, right? This is what it looks like. So let me go back to where we were, which is on the other page here. That x plus h to the n, I'm going to rewrite it. It's going to look ugly, but I have limit, h approaches 0, x plus h to the n, we just said, is x to the n plus n x to the n minus 1 times h plus some number, I don't even care what it is, x to the n minus 2 times h squared plus some number, I didn't care what it was, x to the n minus 3 times h squared plus dot, 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 a bunch of crap. And then I had some number, then there was an x, there was an h to the n minus 1 plus the very last one was h to the n.
On the n minus 3, you have h squared. Shouldn't it be h cubed?
Yeah, sorry, that should be h cubed. Thank you. Right there, h cubed. So everything I wrote there was just what we did on Pascal's triangle, right? All of this is just this piece right here, right? What do we still have to subtract from it?
X to the n.
X to the n. So I need to subtract from that x to the n and then divide all of this by h. Now, this x to the n and that x to the n cancel, right? They kill each other off.
And then every other number can have an h factored out.
every single one of these, right? Every single term that's left has at least one H, right? Right, this one has an H, this one has H squared, H cubed, H to the fourth, H to the fifth, blah, blah, blah. The last one is H to the n. So they all have at least one H, don't they?
But then the H's go to 0, so it's only going to leave that left one, right?
Yeah, I'm gonna factor an H out. I wanna do this right. So in the numerator, I'm gonna pull an H from everything here. One H out of each of those. So when I pull an H, what happens when I pull an H out of here? What am I left with?
In x to the power of n minus 1.
That looks familiar.
Yeah.
Plus, okay, question mark. Now x to the n minus 2. I pulled one H out, right? But I still have an H. Plus another question mark, x to the n minus 3. I pulled one H out of this one, which means I still have an H squared. Plus dot,
H
dot,
cubed.
dot, dot, plus something x h to the here. I took one away from this, right? So this will be n minus 2 now. And the last term will be h to the n minus 1. All over h. These h's cancel. And now the very important understanding point, which is that every single term in green, including everything in the dot, 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 everything there has an H, doesn't it? All of those pieces have H's. The only thing that doesn't have an H is this guy right here, right? That's the only one that doesn't have an H. So now I let H go to 0, don't I? I take the limit. And when I let H go to 0, it kills that, kills that, kills that, kills that, kills everything in here. And the only thing left is this. So your answer is n x to the n minus 1.
I might be looking at this wrong, but why does that h to the n? Why doesn't that just become 1 to the n? Factor
Where?
up, far right, one, that one.
Why doesn't it become 1?
Yeah, 1 second we factor on h.
Well, n is the power, right? So like if that was a 5, right? We take one h out, it would become a 4.
Okay, yeah, I go.
Right? If that was h to the 5th, and I said, hey, factor an h out, now you'd be left with h to the 4th. So it'll always be 1 less than the power. Once I pull an h out, it'll be 1 less than that power. Okay, there it is. There's the proof. Now I have good news and bad news. The good news is I proved the power rule to you. Okay, if you buy all that, if you follow it all, okay, I wouldn't ask you to prove that yourself. All right, but I have an option here as your mentor here in calculus. I have an option here of how many of these rules do I want to prove to you? Do I want to prove every single one of them? Because that's going to take me. This was kind of a tough rule. Some of the others are much more difficult to prove. You're going to take a lot more time. So I have to make a decision. How much of this do I want to prove? So this is going to be the only one I prove. This is it. If you want to see any of the others proved, I will encourage you to come to my office hours and I can do a proof there where we're outside of class time. All right. Because it just eats up too much time.
So question, when you say there are others that are more complicated, are you referring to the ones that we looked at before this?
No.
Okay, I was gonna say, because like
Ones
all
we
of
haven't
those seem very simple.
Yeah, the x to like just x, we already kind of did here.
Yeah,
Just take
like
care of
you
X.
did that as a byproduct of this one.
Yeah, and if you do the constant, then when you do the constant, right, this part right here on top,
Mhm.
f of x plus h minus f of x, if your function's a constant, this is the constant minus the constant, which gives you
Yeah,
0.
it did 0.
And that's the derivative of 0. So, I mean, yes, you could do those. Those are simple though. I do
Yeah,
this
I
one
was-
because it shows how you can't do this one easily. You have to use that Pascal's triangle to be able to get what this expression turns into.
Okay.
Okay, so we have to move on. All right, we have now established the almighty power rule. We've proven it. We're happy. We continue. The only thing, just so you don't like freak out here, the only types of things I'm going to be asking you is stuff like this, okay? I'm not going to ask you to do a limit proof of the power rule, all right? All right, what's the next rule? The constant multiple rule, not to be confused with the derivative of a constant. It's the constant multiple rule. So what is this rule saying? Let me go put it on a different page. The constant multiple rule says this. Say you're trying to take the derivative, and what you're looking at is a constant in front of a function being multiplied. Okay, I'll give you a specific example underneath this, just so you can see what I mean. Let's say we have a function 5 times x to the third. Does everybody see that you could look at 5 as being a constant times x cubed as being some function of x? Y'all see that?
Yeah.
Now, I know that I already told you that the derivative of a constant was 0, right? I already told you that. But that was a constant by itself. If that constant is attached to a function like this, then the derivative of it is not 0, okay? It is, what's going to happen, the rule says this. This is going to turn into the constant times the derivative of the function. Essentially what this says, and this is the way I always tell my students, what's happening in this rule is that constants come for the ride. The constant's going to come for the ride, all right? It's not going to change. It's just going to remain itself. It's just going to come along, tag along, and be there at the end. So if I'm trying to take the derivative of this, I have to recognize that the 5 is being multiplied in front. So my answer is, well, 5 is just going to come for the ride, all right? Here it is. It's still there. Nothing happened to it. But then times, now I take the derivative of that other piece. And the derivative of x cubed is 3x squared. You use the power rule there, right? And then you can multiply the 5 and 3 together, and you get 15x squared. Some people like to just say, hey, the 3 came out, right? This 3 came out and multiplied times the 5 and became a 15. So 3 hits the 5, becomes a 15, and then you reduce the power by 1. That's correct to do it that way. I'm just showing you the rule. The rule says the 5 comes for the ride. You do your power rule, and then you can put them all together. Do not do this, okay? Do not say that the derivative of this is 0 times 3x squared, so your answer is 0. Because what you're doing there is you are making up your own rules. You are saying that when you multiply two things together, that you can take the derivative of each one separately. Nope, you cannot. You're not allowed to, all right? But if this is a constant, if it's a constant, then nothing happens to it and it comes for the ride. I'm not going to prove it to you, but again, you can see the
I have
proof
a
of that.
question.
Yes.
How do you know if it's constant or not?
If it's just a number by itself. That's what a constant is. A constant is just a number.
Any number, negative,
Any
positive?
number, negative, positive, fraction, pi, e. It just can't have a variable in it.
So it's not a 0.
No, 0 is a number. But if
Oh.
this was 0, then the whole function would be 0, right?
Okay.
So then it would be, what would that be? What would be the derivative of the 0 function? Well, 0 is a constant, right?
Yeah,
the
so would it
derivative
just be
of
0?
Just be 0. But that would be kind of like I would never put 0x cubed, right? I mean, like 0x cubed is 0. So why would I put the x cubed there? Okay, let's try something. You try. I'm going to give you a problem to try and find the derivative of. let's say f of x equals -4 over x. Find f prime. Use what you've learned so far. I'll give you 17 seconds. No, I'm kidding. I'll give you a minute or two. I'm going to go refill my drink. All right, so did I confuse you with this one, or how did this one go for y'all? Who had trouble? Who had trouble?
It's tricksy, but I think I have it.
Emily, you said you had a little bit of trouble. Hunter, hold tight. If you've got, I'm looking for someone who's struggling with it. Emily, you raised your hand?
Well, I mean, I don't know. You said, I don't know. I'm like still kind of confused about all of this. I don't know. It takes me a while to get it.
Okay, so Emily, you see a quotient, right? Have I told you how to take the derivative of a quotient yet?
Well, I don't think so.
No, I haven't, right?
Yeah.
So the best hope you have is to move that x up to the top.
Yeah.
Can you
So
move that
what
x up?
I mean, like, can you make it like
from the perspective people
x to the power -1? But I don't know. Is that even like something
Yeah,
you can
that's
do?
right. That's right.
Oh, you
Make it
can?
x to the -1, just like that.
Oh, okay. I thought that would. Okay. Never
No,
mind.
that's right.
Um.
And now you have a constant in front, don't you?
Yeah. So
And then this
would
you
it
can
be?
do.
So it'd be like what, like -4, and then you would do like that
Yep,
constant
yep.
thing for it. So it's like -1x, and then like I guess -1 -1.
There you go. Exactly. Perfect. Okay, so let's see.
In my life,
Oh,
at a point like that in
You're
my
good,
life.
but I'm going to mute you because it's loud. I know you've got a crazy environment over there. So let's see what Emily did. Emily brought the x up to the top to make it x and -1. Realized that you have a constant here, right? Times some function. Constants come for the ride. So the -4 just comes for the ride. There it is. And then Emily did the power rule on this, right? That's power rule. And so the -1 came out, and then still have to subtract 1 from -1. So -1 take away 1 is -2, isn't it? And you multiply those two together, and that gives you +4 x to the -2. That's your derivative.
Can't that be 4 over x squared?
Absolutely. Both of those are correct.
I like getting those negative exponents out of the question because
Yeah.
they're awful to actually deal with.
Yeah. So we kind of have a weird love-hate relationship with negative exponents in calculus, because in calculus, you actually like exponents more than you like fractions, because when you take derivatives, you can use the power rule, right? Like, it's better to be dealing with x to the -2 if I want to take the derivative than to have 1 over x squared. So we actually prefer the exponent, even if it's negative, we're happy with it. because we will be doing, remember, we're taking the derivative, right? This is the derivative. What if I asked you for the third derivative?
Yeah, so I could just keep taking the derivative of,
That's right. You just keep going. So it would be better.
in which case we wouldn't convert it down.
That's right. You would be better off leaving it like that, right? And then doing your derivative again, and then doing your derivative again. So
That'd be negative 8x to the negative third.
at
the
negative
second
third.
derivative,
Yep.
I think.
Okay, so here's one. Here's another one for you. What if f of x equals, this one for some reason trips people up. So give me the derivative of this one. I'll give you a minute on this one too. Maybe just a minute. Okay, so I always see like crazy stuff with this. Let me show you, this is completely wrong. Right? What did I do there?
You just took the derivatives
Derivative
of
of
the
the top
both
and
of them
bottom
separately.
separately.
I'm bottom. That's right. You're fired. Get out of here. That's not, you're not allowed to do that. Okay.
Yeah, I didn't do that.
All right. So now I know some people might try and move this 5 up. Just watch. I'm just going to rewrite this as 1/5 x to the 4th. There we go. Okay. This right here, this expression, this is the exact same thing, right? A 5 on the bottom is the same as multiplying by 1/5 out front, which is why you'll see me, like I very, very seldom ever leave an expression like this. I'll always write it with a fraction out front. And the reason is because once you get into this calculus brain, you always want to have your constants out front and x to a power. Like that's what you always want to see. So if you have to take a derivative, or if you have to do an antiderivative in Cal 2, it's just so much easier to work with. So once you're here, you have your constant, you've got your function. And so when we take the derivative, the constant will come for the ride. 1/5 will just be there. Then I do power rule on that, 4x cubed. Now I can multiply the 4 and the 1/5 together to get 4/5 x to the 3rd.
Once again, 4x to the 3rd over 5 would also work, correct?
Yes.
How did you get from x to the 4th to x to the 3rd?
Okay, so I took the derivative, right? I took the derivative. So when you take the derivative of this, that gives you this. I'm using the power rule here, which means the power of 4 comes out, right? And you subtract 1 from the power. Yes, Isabella, that's the rule that I proved. Now we use it. Okay.
I got it. Thank you.
Yeah, I guess just pay attention to that right there, that prime mark. That's me signifying that I'm actually doing the derivative now. Okay, let's do the next rule, and then I'm going to give you one to work on. Okay, this rule, it looks crazy, but it's not that bad. All it's saying is that if you're trying to take the derivative of two things that are either added or subtracted together, so you have multiple terms, okay, that you are allowed to do them individually and then just add or subtract the answers. If you have addition or subtraction between two terms, you may take the derivative of each term separately. You can't do that for a quotient, right? For the quotient, you cannot do the top and bottom separately. That's a big no-no. But if it's plus or minus between two things, you can. This is called the sum or difference rule. And it actually works if you have 3 things added together or subtracted, or 4 things added or subtracted, or 5 things, or a million things. Doesn't matter how many you had. If there's separation with addition and subtraction, you can do them individually. It's called term by term differentiation. So I'll give you an example of this. So let's say we have a function f of x equals x squared minus 5x plus 1. That's a quadratic function. If we're asked to find the derivative of this, then I recognize that I have 3 terms, 1, 2, 3 terms separated by the subtraction and addition. So when I take my derivative, I can do them individually. So when I take the derivative of x squared, I can use the power rule, can't I? So that just becomes 2x. 2x to the first power, but I don't need to write a 1 up there. I can just leave it, right? Minus 5x. Okay, here's a constant attached to the function, right? There's multiplication between those. So the constant comes for the ride.
Doesn't that x just become 1?
And the derivative of x is 1. And then plus, now I take the derivative of 1, but 1 is a constant, right? So the derivative of a constant is 0.
0.
If the constant's by itself, it's 0, right? Which it is here. So my answer here is 2x minus 5. Questions?
Why can't we do this instead of the last 2 lessons?
Yeah. Once we get rid of the limit, right? It's
Yeah, this is so much nicer and cleaner. I'm excited to like come to hate it because there's so much other crap surrounding it.
yeah. All right. You take a minute, find the derivative of that. All right, so how did this go?
Went all right?
You know, Raquel, did you get it?
Yes.
All right, go for it. What do you got?
I got kind of stuck on like the first part, but I got -4/2x to the third
Okay, that's right.
plus 9x squared
Yep,
minus 5.
perfect. Okay, just turn the -4/2 into -2.
Okay.
Right, so that just becomes -2. Perfect. Good. Good, good. So that's just do them individually, power roll on each one, right? Constants come for the ride. And now while you were doing that, I went ahead and so that we don't lose sight of what we've got now, I graphed the original function and its derivative. Okay. This should be it. The red one is the original function, and the blue one is its derivative. And let's just check it. Let's just check it. Everywhere that I have on the red one a horizontal tangent line, right, like this, my dotted function should have an x-intercept, which it looks like it does, right? Right there, right here, right, oops, right there, right? It looks good. If I take one little region, like from here to here, my original function is increasing there, isn't it? Between this point, whatever that is, and between here, whatever that is, my original function's going up, which means my derivative function should be above the x-axis, which it is. And we could check the rest of the areas, but that wasn't that hard to do, was it? I mean, with the
No,
rule,
that would have been
wasn't
an
that hard to
absolute
do.
bastard with our other form of doing it.
Yeah. So we have a very powerful tool in our hands now. This power rule is tremendous. Just again, so we don't lose sight of it, because I don't want us to take for granted what we have here. If I had given us this function without today's lesson, then I ask you to find the derivative. You would have to do the limit as h goes to 0, and then you'd have to plug x plus h into this. So it'd be -1/2 x plus h to the 4th plus 3 times x plus h cubed minus 5 times x plus h. Then subtract from that the original function. And then all of that over h. And then, you know, enjoy. You would have to expand that to the 4th power, 3rd power, right? Distribute everything out, collect like terms, get things to cancel, factor an h out, and then let h go to 0. So we really have saved ourselves quite a bit of time and effort, haven't we, with this?
Yeah, that one would have been horrific to do like that.
It would have been doable though.
Yeah, very doable, but
it would have
awful.
been doable, but it would have just, yeah, it would have been terrible.
Massive room for error just because of the huge amount of arithmetic that would happen.
Yeah. Okay, now this next one, it's a rule, you need to memorize it, okay? The derivative of sine of x is cosine of x. What? What? The
That actually makes
derivative
a lot of
sine of
sense.
x is cosine of x? Let's see what we're saying. If we graph sine x, right? Let's go and look at sine x here. I don't like this. Let's go -10 to 10, and then 10, and then let's go 10 here like that. Okay. So here's a graph of sine of x, right? Now I'm going to graph cosine of x. All right. Let's look at where the sine function. So you know what? I think I've done this backwards. Hold on a second. If I want to stay consistent with the colors I've had today. So this will be green. This original one will be red. Green dotted dot. Okay, so the red function is the sine function, right? Let's look at where that sine function has tangent lines that are 0. So that will happen here, right? Down here, here. Let me do one more thing. Step pi over 6. There we go. Okay, so no, that didn't work. Pi over 12. Will that be better? It's good enough. No, I better just do pi over 2. Pi over 4. Will that give them to me? There we go. Pi over 4. There we go. All right. So look at where the sine function has flat tangent lines. The derivative of that, right? The derivative then should go through the x-axis there, which you can see the derivative here goes through here, x-intercept, x-intercept, x-intercept. And now let's focus just on this region here. We are increasing there, aren't we? Which means that the derivative should be above the x-axis there, which it is, right? And then when we get to this region here, the original function is going down, oops, down. So that means the derivative should be negative there, which it is. And then so on and so forth. So it's pretty amazing, but it's true. Yes,
Question, just looking at this, would the derivative of the cosine be the sine?
That's a good question.
Because looking at the graph.
Let's do that. Let's do that. Let's look at the graph. Let's first make sure everyone's on board with this stuff. I'm not proving it to you other than visually, all right? You can prove this using the limit definition, but again, that's an office hours thing because it takes too long. It's a great proof. You have to use a sum and difference formula from pre-cal to do that proof.
Oh God.
Yeah, remember those formulas from pre-cal?
I don't remember
they
what they
exist?
look like, but I remember them existing.
Yeah, they're there. So everyone, the derivative of sine of x is cosine of x. All right. Now the question is, does it work the other way around? So let me see. I'm going to switch these. I'm going to make the sine our green dotted one and make this one our red solid one. So the red function, right? The red function is cosine. The green one is sine. Let's see if it matches up. Let's go to the red function. Let's look at our flat tangent lines here, 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 right? There's no one back here. The derivative, does it go through there? Do we have x-intercepts at those points? We do, right? We do, okay. Now let's look at the region between here and here on the original function. It's going down, isn't it? Which means the derivative should be where?
In the negative.
Below, right? Below the x-axis? Where is it? Where's this sign? Where's the green up here?
Love
It's
it.
up, isn't it? It needs to be down here, doesn't it? So it doesn't match. And then if we go over here to this side, our original function's going up, which means the derivative function should be above the x-axis, which means it should be up here, like that. But wait a minute. Isn't what I just drew here, isn't that really just the sine function flipped over? Yes.
Is that what the integral is?
No, no. Let's look at the formula. The derivative, okay, derivative of sine of x is cosine x. The question was, is the derivative of cosine of x sine of x? And the answer is no. The derivative of cosine of x is negative sine of x. It's the reflection of sine of x over the x-axis. So please pay attention to that negative right there.
See, that's a really interesting one.
Yeah, that one's pretty, I really like the relationship that the derivative of sine is cosine because it's just like so awesome. I kind of wish it worked the other way too. I wish the derivative of sine was negative cosine. Sorry, derivative of cosine was also sine, but it's negative sine. So
Not everything can be as nice and
Yeah.
simple as
Yeah.
some of them are.
yeah, I like the next one, tangent, right? What's the derivative of tangent, right?
That one's going to be really fun.
Well,
Oh,
here are the
God.
derivatives of the remaining trig functions. Okay, we need to just know these. So I'll tell you what you need to know. Everyone here has to know that the derivative of sine of x is cosine of x, all right? That needs to be up here. Derivative of sine is cosine. Everyone needs to know the derivative of cosine is negative sine. That's got to be up here, all right? And everyone needs to know that the derivative of tangent is secant squared x. Okay, you got to have those up here. The other three, you can have a little more time to learn those. But when you get to calculus 2, you should know these up here also. Maybe not right away, but you will need them.
Question, since it's been a hot minute, secant squared x, does that mean after I take the secant I square it, or I square the x before I take the secant?
If the squared was right here above the x, I'd square the x. We put the 2 here intentionally so that you know to square the secant function.
Cool. I just wanted to verify. I
Oh,
was
that's a
thinking
good
that was
question.
probably correct, but I wanted to check.
That's right. That notation, when we write secant squared x, what we mean is secant x squared.
These look really
Not-
similar to the inverses from trig.
Not this. That's not the same thing. In fact, if we wanted to do this to be real safe, we'd put the x squared in parentheses like that. So these are not the same. What was that? I'm sorry. I heard something. What?
Just saying, these look really similar to those like inverses or whatever from trig.
Yeah. This
I
one's
know what
weird.
you're talking about. They do look like that.
Let's do this. I'm going to go to the calculator and or to the graphing utility and graph that. I think that's worth looking at. Let's have the computer graph tangent x. Okay, that's what tangent looks like, right? That's our beautiful tangent function. Has a bunch of vertical asymptotes everywhere. All right. Now let's look at its derivative. Let's talk about it. What can you tell me about the derivative? Just right off the bat. The derivative should always be what?
Secant squared x.
Well, I know it's secant squared x, but in terms of, think of the slope of the tangent line. If you go to anywhere on the tangent function, what's the slope of the tangent line have to be?
Positive.
Has to be
Yeah,
positive,
it's all going to be positive.
which means the derivative better always be positive, right?
Yeah.
And if I look, let me do one more thing. X equals pi over 2. And let's go x equals negative pi over 2. These are vertical asymptotes. Right? I have vertical, there's more, okay, but I'm just going to graph those two. Think about what we're saying here. If we look at the slope of the tangent line on the tangent function, the slope there looks like it's probably about what? What is the slope of that?
Looks like it might be floating around 1 at that point.
About 1, so it's positive, right? As I move to the right, what happens to the slopes of these tangent lines?
Gets more extreme.
More extreme, which means I get bigger positive numbers, right?
Yeah.
So my derivative should go like this. And then when I go this way, it's still positive, isn't it? But really steep. So it should do
Yeah.
this also. So let me graph it. Let me graph the derivative. Secant squared is same as 1 over cosine of x squared. There it is. The green graph tells you the slope of the tangent line on the black graph at every point. It's pretty awesome if you ask me. I mean, it's pretty awesome. But again, I'm not proving this one to you, okay? I'll prove it to you later, but I'll do it a different way. I won't use the limit definition. I'll kind of a little bit.
Quick question, because we've looked at a few, and there were also a good amount in the homework where this came up. The domain of a derivative would be the same as the domain of the original function, correct?
The domain of the derivative must be, okay. It is possible for the domain of the original function to be more than the domain of the derivative, but the domain of the derivative cannot contain more points than the original function.
Okay, so if it's
example.
like there's a vertical asymptote here, the derivative needs to have that same vertical asymptote, just like this has.
It can't, yeah, your derivative cannot possibly be defined somewhere where your function is not defined.
Okay.
A good graph to look at, I like to kind of show an example, is if you look at the square root of x, there's the graph of the square root of x. Is this function defined at 0? Is the original function defined at 0? Square root of 0.
Yeah, it's 0.
0, right? Square root of 0 is 0. So this function is defined at 0. Now, what is the derivative of the square root of x? 1 over 2. Thought y'all were
2 root x.
2 root x, right? That's a derivative. So that's the graph of the derivative right here. And can you see from this picture that the derivative is not defined at 0?
Yeah. It
right? You
shoots
can't
up.
plug 0 into this. So you can see, though, that it's because the slope of the tangent lines are getting more and more vertical here. As you try and get closer to 0, these go vertical. And remember, Emily, we talked about this, right? Your derivative fails to exist when your original function starts to have tangent lines that want to go straight up. Then your derivative would fail to exist. And that's what's happening here. Okay. Let me just see where we are in the notes. That's it. Okay, now let me point something out to you. On your formula sheets, okay, the ones that you can have for our tests, if you go to reference page 5, you will see the rules that we just learned. Okay, you'll see first, the derivative of a constant is 0. We learned that, didn't we? We learned that formula 8, the power rule, that the derivative of x to the n is nx to the n minus 1. We learned formula 2, that constants come for the ride, right? We learned that. We also learned that if you add two functions together, you can take the derivatives of them separately. We learned that if you subtract two functions, you can do them separately. We learned all that today. We also learned the derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent secant squared, derivative of cosecant is this. We learned all those. Well, I tried to convince you of the first two, the others you're taking on faith. So right now, where we stand is everything in yellow is what we covered today. Those are our differentiation rules. What we are going to do next class, and I'm going to start it today, is we want to do the product rule. So how do you deal with it when you have two functions that are multiplied, or if you have a quotient? And we have those rules. That's the next section. And then after that comes the chain rule, the formidable chain rule. Okay. So these two, and then look, there's a bunch of other rules on here. What's that? The what? I didn't hear you, Nathan.
No, that thing is horrible. I remember that thing being
chain rule?
god awful. Yeah.
I have heard of the chain rule.
The chain rule is the one that separates the, I don't know. I don't want to be, yeah, I don't even know what to say. It separates the, yeah, I'm just going to shut up. Okay. All right, here we go. We are going to talk about what happens when you have a product. So your quiz, okay, your quiz today that everyone took at the beginning, I'm going to share with you what functions they were. Okay, so let's look at these one at a time. Which one do I want to look at?
So real quick, are we in 2.4 now?
Yeah, informally. We're not going to open up the notes. We're just going to talk about it. Yeah,
Okay.
we are going to be going into 2.4. We're done with 2.3. Okay, so the function that we're looking at right now is the function. Come on, Robert. Okay, the function we're looking at is this function, f of x equals x times sine x plus 2. Okay, so jot that down. Got it? Okay, that's the graph of x times sine x plus 2. There it is, all right? Now, if I take the derivative of this, what I know so far I can do is, because I see a plus sign, I can do this and this separately. Do you understand? I can take the derivatives of those individually, which means that I need to take the x times sine x, I need to take its derivative and then add to that whatever the derivative of 2 is. With me? Do you understand this notation? I'm taking the derivative, I have an addition sign, so I'm doing derivative of each of these individually because the rule tells me I can do that with addition. Now the derivative of 2 is what?
Would be 0.
0. Okay, that's a constant. That's the easy part. This, though, is a product, right? We have a product there. And we have not learned how to deal with the derivative between two things that are being multiplied. If they're being added, we can do them individually. If they're being multiplied, can you do it individually? That's the question, right?
No.
Yeah, I mean, we're not, but let's just see. If we could, right? Let's just say if we had x times sine x, life would be beautiful if the answer to this derivative of that was 1 times cosine x, wouldn't it? Wouldn't that be nice? You just take the derivative of x, which is 1, then the derivative of sine x, which is cosine x. And the question is that right? Right? I don't know. Well, let's graph it. So I would like, there's the original function. I'm going to graph cosine x, right? That's what we wish it was this, right? 1 times cosine x, which is cosine x. Let's see if it is. Here's the graph. All right, so let's start looking. Slope of the tangent line here is 0. Slope of the tangent line here is 0. Slope of the tangent line here is 0. I look for an x-intercept. Crap, I don't have one. Go down here, no x-intercept on the dotted one. Go down here, no x-intercept. What? It's not right, right? Let's go a little further. If I analyze what's going on right here, my original function's going up, right? So my derivative should be what here?
Above the x.
Of the x-axis.
Okay, it is until right there. See, but right here, do you see? Right there, I should still have positive answers here, but I'm getting negative now. This function's all out of whack. It's not correct. You see? It's not correct. Now, what is the correct answer? The correct answer is this function, sine x plus sine x plus x cosine x. Now, I'm not going to show you how to get that yet, but let me just show you that it does work. Okay. So everywhere that I have flat tangent lines, x-intercept, x-intercept, x-intercept. See it? If I analyze what's happening in here, my derivative should be positive there. Beautiful. If I analyze what's going on over here, my derivative should be negative. Yep, it's down there, it's negative. If I analyze what's going on right, I'm running out of colors. If I analyze what's going on here, it's going down, my derivative should be negative. It is. Everything is perfect. Kind of understand? So the real answer to this, okay, the real answer to this is not all this. It's not this. This answer is sine x plus x cosine x. That's what it is. And the question is why, right? How? And that's what next class will be about. Okay, and that will be called the product rule. And we'll learn it next time, okay? Product rule.
All right.
Stay tuned. This is where things start to, once you get to product rule, quotient rule, chain rule, where things don't behave naturally the way you wish they would, is when students start to have problems because, well, it doesn't do this like you want it to do this, but it doesn't. So, okay. So for homework, I would suggest you do the 2.3 stuff. Okay. Do the 2.3 basic differentiation formula stuff. Yeah, let me see if there's anything on there I would tell you to not really worry about. We're at a point in this class where we have these rules now, which is going to make our life better. But now everything starts to build on itself very rapidly. So you have the basic rules, then you have the product rule next class, quotient rule, chain rule. And to be honest with you, that's it. Those are the only rules in Cal 1. I mean, that's it. There's other specific scenarios, like what's the derivative of e to the x? Like we haven't talked about that. We haven't talked about exponential functions, right? But so there's certain special scenarios, but the main ideas in Cal 1 are product rule, power rule, product rule, quotient rule, chain rule. Those are the main rules. And so if you don't understand the basic rules from today, product rule and quotient rule, you won't be able to do. And if you can't do product rule and quotient rule, you can't do chain rule. So it's very important that you can keep up with the work. It's not like continuity. Like right now, if you still don't get continuity, you're okay. Like you can be okay. But if you don't understand basic differentiation, there's no way you can do product rule. No way. All right. So it's important that you do this homework and that you understand it and ask questions before, you know, we meet again. So wait a minute, hold on, I'm looking in the wrong section. 2, 3. Just want to make sure there's nothing in here. Yeah, this looks fun. There's a few that ask for the first and second derivatives. There's some here that ask for the equation of the tangent line. So you're gonna have to draw back on some things that we've done in the past. But the thing is, you now have this new tool, right? These tools, power rule and, you know, constant multiple rule and all that. So see how it goes. I think there's a few on here you're gonna have trouble with. I think number 19, number 22 specifically, you might have an issue with. See what you can do. All right, enjoy, have a great day.
You too.
I have a question.
Yep.
You said next Tuesday is the test.